So we have our IZZ already. Okay, so now we can plug everything into the formula. So let's look at the formula first. Okay, so the formula states that stress X is equal to Px over A, right, plus by Mz over Izz multiplied by Y. Okay, so we know that Px is equal to 400 Newton. And we are also aware that A is equal. So if we look at A, we have calculated the area. In fact, that this is our area, our summation of area. So the area will be 104. It will be equal to 104 times 10 to the power minus 6. Okay, times 10. So 104 times 10 to the power minus 6 meters squared. Right? And then the next thing we look at is equal to mz. What is our moment about z? So our moment about z is going to be, so let's look at over here now. Okay, so the moment of z is this distance. Okay, I'm going to use a different color. It's this distance, right, plus by the distance to the centroid. Okay, plus by the distance so the distance to the centroid, I'm going to call this point E, right? So it's equal to 50, or in meters is equal to 0.05 plus by E. And E corresponds to 8.154 times 10 to the power minus 3. So this is also equal to our what? Equal to our E. So from here, this will be equal to 0.05 plus by 8.154 times 10 to the power minus 3. So this will be equal to 58, or 0.05 8154 meters. Now, remember, what did I say? Take the datum from the what? From the top. You just need to add up with the E. If you were to take your datum from the bottom, right? So if you were to take your datum from the bottom, you'll find out that if you take the datum from the bottom, it will be equal to 20 minus 8.154. You will find out that this distance will be equal to 11.846. And to find this distance over here, to find this distance, sorry, down here you have to multiply by P. I do apologize. Too excited again. If you were to take, so I'm going to write down here, if you were to take datum at the bottom to find the centroid, you have to remember this now. So your P, your MZ is equal to P multiplied by 0.05, right? Plus by 20 times 10 to the power minus 3 minus by 11 minus by whatever it was, minus by what? 11.846 times 10 to the power minus 3, right? Can you see this extra step over here? Right? That extra step over here, sometimes if you forget, you'll be in trouble. You might make a mistake by just simply what? You might make a mistake. It's so easy to make my mistake like this is equal to 0.05 minus by what? 11.846 times 10 to the power minus 3. What will happen is this will be wrong. Okay, that is why my humble, sincere advice is this is where the centroid is. Your datum should be taken on the same side as your what? As your load P. Okay. Before I proceed, any questions, please?
I have a question about the location of the centroid.
Yes.
Why are we not? So if we're looking at just the section, the location of the centroid makes sense. But if you're looking at the side view, why do we not include the vertical parts of the clamp in the geometry?
The vertical part of the
clamp, like the where the thread is and
okay.
the
Okay, so wait, let me try to think about. So why don't so you're asking me why the neutral axis is not from the applied force? Is that your question?
no, why when we're calculating the centroid, it's
Yes.
based on area. Why don't we care about the uprights on the clamp?
You mean this position and this position?
Yeah.
Yeah,
And
or this, right?
yeah.
Right. So we did not care about that because that will induce the moment. We only are interested about this cross-sectional area. Does that make sense? Because the failure is going to be at section AA, for example. Okay, remember what I told you? You calculate your you calculate your stress view based on where your structure will fail. Okay, so you're interested in this region. That's why you only need to calculate the cross-sectional area, or you only need to consider this cross-sectional area.
Okay.
Now, the P will then be inducing based on the structure. So the moment will be based on the structure, the offset of the structure, and the centroid. Does that make sense?
Yeah. Okay.
Okay, that makes sense. Good. Okay. Initially, I thought I did not understand your question. Give me time, okay? Sometimes I need to to think about your question, and please be patient with me, okay? In terms of explanation, right? So now we have everything sorted out already. So the formula, regardless whether is it at point A or point D, this is always a constant, right? This is always a constant. Okay. And then regardless of whichever point, this term, right? This term is also a constant. And the location of the point, the y, is only your varying. This is your varying part. Okay. So the first thing we can calculate like what is our constant. So we can calculate what is our px over a. So our px over a is equal to 400 divided by the cross-sectional area, which is 104 times 10 to the power minus 6. So 400. So it's equal to 3 point. So it's going to be tensile positive 3.846 times 10 to the power 6 Pascal. So this is what we classified for axial loading. Okay. Then we can calculate our moment about Z. So our moment about Z, the force applied is 400 multiplied by 0.058154. So this will be equal to 400. So it's equal to 23.262 Newton meter. Right. So now we can directly calculate stress X at point A now. Okay, stress X at point A. So the first term, Px over A, we know this is going to be positive 3.846 times 10 to the power 6. My over I, so this is the moment is 23.262. The second moment of area is equal to 3.8802 times 10 to the power minus 9. The y, right? The y is from the centroid. So you go back here. This is our A. So this distance is our y for point A, right? So this is equal to 8.154 times 10 to the power minus 3. Now the thing is of concern, what sign is this? But we have done the analysis already. There's nothing to fear. We have done the analysis. So if we go to the top, or we go to for this analysis, we know that this is going to be what? At point A, like what I've written, is going to be tensile. Okay, the bending is going to induce a tensile. So this is going to be plus. Okay, this is going to be plus. I hope you guys are not getting a headache me moving the notepad from here to there to here. Okay, so this will be equal to 23.262 times by 8.154 power minus 3 divided by 3.8802 power minus 9 plus by 3.846 power 6. So it's equal to 52.730 positive 52.730 times 10 to the power 6 Pascal. Okay. Right. And then we can also calculate our stress X. So let me write out the value, okay, before we go there. So this is equal to positive 3.846 times 10 to the power 6 plus by the moment is equal to 48.884. Okay, 48.884. Now my pen is not working, my bad. Okay, 48.884 times 10 to the power 6. So this is where you get your positive 52.730 times 10 to the power 6 Pascal. Remember what we spoken about earlier, right? So this is induced by your axial force, and this is induced by your bending moment. Okay, so what we realized, sorry, you can hear the garbage truck, I know that. So what you realize that the bending moment, the stress induced by the bending moment is so much higher. So that's why when you want to break something, you don't just do a tension thing, right? You bend, and it breaks, and it's for that reason. Nothing to do like what I said earlier, anger management. Okay, it's logical, right? So the next one we're going to do is we're going to find the stress X at point D. So we're going to look at stress X at point D, and we know that the first term, the axial stress is going to be the same, so it's going to be 3.846 times 10 to the power 6. Now, right, the moment, so let's look at the moment. The moment is equal to 23.262 divided by the second moment of area, 3.8802 times 10 to the power minus 9. And then this is multiplied by the position will be equal to 11 point, we calculate this earlier, is equal to 11.846 times 10 to the power minus 3. And then whether is it tensile or compression, you just look into this diagram over here, right? You realize that we already analyzed that the head end of the bending moment arrow is going to induce a compression. So this will become a minus, right? This will become minus. So this will be equal to 3.846 is in tensile minus by 23.262 times by 11.846 power minus 3 divided by 3.8802 power minus 9. This will be equal to 71.017 times 10 to the power 6. So the outcome of this will be 3.846 minus 71.017 is equal to minus 67.171 times 10 to the power 6 Pascal. Right. So this is, here is where we are now. Okay. So the next thing that we're going to do, okay, so we calculate our stresses. The next thing we're going to do is we're going to find the position of the neutral axis. Okay, so the next thing, but before I carry on, Anyone have any questions up to here, please? Anyone?
Yeah, I have a question.
Yes, please.
If we're gonna calculate the stress at point B, would we just have to change the y value in the
Yep.
bend moment? That's it.
Yep. So good question. So I'm going to do further. Okay. So I have a question. What is stress X at B? So stress X at B, right, is the same thing. So you get 3.846 times 10 to the power 6. Now, the moment, right, at point B, right, this is your point B, yes or no? And you know that this the centroid is 8.154, right? The centroid, right? So it's pretty far away from the what? From the centroid. So that's why you can assume it to be a what? Same as stress A. So it's going to be a compression. Sorry, it's going to be a tension, not compression. So you can over here you do a plus, right? Plus again the same thing, 232.262 divide by 3.8802 times 10 to the power minus 9, and then you multiply by the y. So you know that the thickness is 4 millimeters. So 8.154. So it's equal to 4.154 times 10 to the power minus 3 from the centroid. Okay, from the centroid. So the outcome of this is going to be 23.262 times by 4.154 power minus 3 divided by 3.8802 power minus 9. So it will be equal plus by 3.846 power 6 is equal to 28.749 times 10 to the power 6 Pascal. Okay, let me do it again. Why 4.154? Because we have to compensate, we have to know the distance of point B. Okay, so plus by 3.846 power 6. Yep, it's correct. Does that answer your question? Okay, that's clear, right? Right, so okay, thank you. So the next thing we're going to do is now we're going to sketch. Okay, now we're going to sketch the position of the neutral axis. Okay. Before I go on, I will write something up. So we want to find the position of the neutral axis where stress X is equal to 0. Okay. And as I mentioned earlier, this is eccentric loading. So the centroid is not equal to the what? Neutral axis. Right. So there are ways to do this, okay? Let me show you the mathematical way of doing it. So stress X is equal to P over A minus by M Y over I. Right? So this is a standard equation there. So we know that stress X will be equal to what? 0. Okay, so 0 is equal to, so this is, I call it my equation number 1. So 0, so we're going to substitute, yes, substitute stress X is equal to 0 into equation number 1. So you have P over A is equal to My over I. And then finally, Y is this Y that you want to find out is equal to Pi over Am. Okay, so this is the position of the neutral axis. Okay. So if you want to memorize this or you want to go for it, go. So if we were to calculate, okay, so as I said, I'm not bothered to use this formula, but I'm just going to try to see what value I get. So P, like what we have calculated, is equal to 400